Okay. Well, so we've covered energy, we've covered power, we've looked a little bit at aircraft engines. The next section here at 8.3 is the diesel or compression engine. And here's a picture of Rudolf Diesel himself. One of the most interesting things in this book, it talks about how an early engine, you basically just had like this explosion going off to see how far you could send a mass into the air. But I guess what we're looking at here is the oil engine. But the diesel engine is important to keep in mind that the gases get hot enough from compression that you don't need a spark plug. They just automatically ignite at the temperature inside the engine.
But don't they have a glow plug or whatever?
There will be what's called a glow plug to get the initial temperature up there, right?
Okay.
So you don't have to start it cold. Exactly. Okay, here's an oil engine. Again, this is just burn oil. And a big flywheel out here, and you could see you might think of this as an early analog to the grid scale turbine engines that we have. So you could make electricity with this. You could hook it up to a drive shaft, pump water with it. Sure, lots of different things. You don't see too many oil engines anymore. Sometimes for heat, but not so much for power. Yeah.
So I recently watched a documentary called Fuel.
Yeah.
And in there they talk about Rudolf Diesel and how his original engine was actually built to run off of biofuel.
Oh, sure. Yep.
Like ethanol made
Yep.
from corn, which
Yep.
is basically moonshine.
Yep. That's
And
right.
emission came around.
Head boiler.
Mm-hmm. Yeah. Well, I think yeah, and in some ways it's sort of easier to extract fuels from crops. It's just that yeah, it's just that now you're sort of limited by the growth cycle. So, and I don't know if I still have Shramsky. Yeah, I have Shramsky here.
Innovation sparks legislation.
Yeah, exactly. Isn't that
No.
I have shrimp, but this is the reality we're facing. I mean, this is how much sequestered carbon there is left on the planet. I don't know if I showed you the Shramsky paper or not. And so, yeah, in a sense, it's like, hey, let's skip the whole biofuels thing and just go for the good stuff underground. But the day is drawing near where it's not going to be there anymore. Yeah.
A couple years ago, I read an article in a coffee magazine.
Yeah.
It's like coffee from around the world, or
Uh-huh.
whatever.
Yeah.
And in there, they were talking about a plantation somewhere in South America where they actually started growing macadamia nuts
Uh-huh.
on the side of their plantation where they couldn't really grow coffee well
Yeah.
because of the shading or something.
Sure.
And they actually used this particular type of macadamia to make biofuel.
Huh.
And they have their own biofuel processor,
Huh.
and then they literally power their whole plantation off of the macadamia nuts
Yeah.
that they grow.
Yeah.
Pretty
That's a
cool.
yeah.
Put that out there.
Pretty energy dense. No, and I think we see that a lot, just, a competition between food and fuel. All right. All right, so this guy's figure 810. This is fuel consumed by the British railways. That's a pretty telling figure in terms of the phasing out of the, really the external combustion engine, steam engine. And now we use some oil and some electricity. This is a good question here. The primary energy. The question is, well, where's that electricity coming from? And if it's on the grid, it's coming from everywhere. It's coming from hydro. It's coming from nuclear. It's coming from coal. It's coming from solar. It's coming from wind. But this blue trend will only continue to rise as the fossil fuels diminish. There's a smart car. I had the pleasure of driving one through the mountains of Italy one summer in 2004 or 5. You can literally reach out the window and your hand will touch that wheel. I mean, it is that small. I mean, it's like right there. It's kind of like patting your rear. It's just right there.
Sitting on top of it.
Fun to drive. Okay, Petrol and diesel engines, this is 8.4, reducing pollution. Show you this really quick. One thing that can happen if you get too hot, you've got N2 plus O2 becomes 2NO. Very potent greenhouse gas. I'm going to show you one other thing since we're on this topic. You'll appreciate this. Patents, water catchment. Some of these are mine, some are not, but I've just called the partner of this engineer, and there is a patent out there owned by Lockheed Martin. It's expired now, which means it's up for grabs, but here you go. Biofilter for removal of nitrogen oxides from contaminated gases under aerobic conditions. So there are a class of microbes. I think they're listed here. I had another copy where I'd underlined them all. I'm not going to be able to find it here right off the bat. Well, I'll just say culture of denitrifying bacteria capable of converting nitrogen oxides, which we're looking at right there, it's just nitric oxide, into nitrogen gas, carbon dioxide, and water. So it's taking this equation, reversing it, and you've got water and some CO2 coming out. So, and again, it's kind of pick your poison, but because some colleagues and I are looking to actually develop this technology and stick it on cold strip, and then the cycle continues. So we'll see. We'll see what happens. It's food for thought. Because again, atoms and elements are immortal. Okay, now this is why you want to optimize your fuel-air mixture. We saw some photos, some pictures, schematics of internal combustion engines. If you get hot enough, as I mentioned, this happens, and one way to visualize this, the nitrogen bond is a triple bond. The oxygen bond is a double bond. I don't have the numbers at my fingertips, but this is a much higher energy bond. It just takes more energy to break it. And so at higher temperatures, you have higher energies, and you're more likely to break that bond. So
Not Carlo.
so maybe not. Do take a look at this graph. There is a test question on this graph, and what you're asked to do is look for sort of the optimal ratio. So what's going on here? If you're rich, so if you've got too much gasoline in your engine, you're going to have a lot of hydrocarbons coming out. At a 16-to-1 ratio, you sort of hit a minimum or an optimum. This is your NOx. This is figure 813 on page 294. Here's your NOx, and so the NOx hit a peak out here. So really, what you're doing across all these different curves, here's your carbon monoxide. So obviously, if you don't have enough oxygen in, carbon monoxide is coming out because you didn't throw enough oxygen. Here it sort of goes to zero. So somewhere in all of this mess is the sweet spot. So you'd kind of like to say, hey, well, my fuel economy is the best right here. My NOx are going down, but I can't get all the way out here because now my hydrocarbons go up, et cetera. So there's a question sort of asking you to interpret this graph. So that's what each of these curves means. So the air-fuel ratio means that you've got the 18, there's 18 parts air per 1 part fuel. Okay, now here's your jet engine. Now we're at 8.5. compressor, so here's air coming in. MV, so M times V, we have not talked about this, but M times V, the technical name for that is momentum. We've talked about force, we've talked about energy, but mass times velocity is momentum. We talked about Newton's laws. There's another law of physics that says it's just called the conservation of momentum. So if you add up all the masses and all the velocities in the universe, it sums to zero. So whatever's coming in here is going to equal what's coming out here plus the added momentum of the aircraft. So again, here's your combustion chamber. As these gases get hot, as they expand, it's a one-way street. And they'll spin this little downstream turbine, which will actually drive the compressor, which sucks air in faster than it otherwise would, and then out comes the exhaust, and away you go. Going to be on one of these tomorrow. Flying to DC. Yeah. I will. I think I will. I'm going to talk to some National Science Foundation folks about our project. Yeah. Okay, so here's another jet engine manufacturer, and for better or worse, a lot of these technologies are developed, paid for by the military. Here's another. I love this little story. It says, here's Frank, we were just talking about patents a little bit. Frank Whittle developed his jet engine in England. He had to allow his patent to lapse because as a Cambridge University student, he couldn't afford the £5 to renew it. I found that a little surprising. Is it really? I mean,
Talk to a buddy.
$5? Yeah, I mean, come on, take a little micro loan.
What year was that?
What is this looking at? I'm guessing the 30s and 40s.
Well, $5 went a long way.
Yeah. Frank Whittle. Yeah, 1930, he designed and patented it.
It's right during the fan or the decibel or whatever too.
Yeah.
Well, he got whittled down.
He got whittled down. All right, I thought we'd go through these equations on 300. It's not. It's go through that on your own. I'll just sort of scratch them out briefly since we're running a little bit low on time. But it does start with Newton's second law, F equals ma. So this is if you really want to accelerate. They go on to write that A equals delta V over T. So this equals the velocity of the jet. That's actually, this velocity right here coming out of the jet minus the velocity of the aircraft. So if that jet were not traveling faster than the aircraft, it wouldn't go. And here's the time. So it says taking a particular mass, m in kilograms. Newton's second law tells us that the force to create acceleration is just force equals mass times v jet minus v aircraft over time. It also goes on to say that the force for an aircraft is 200 to 400 kilonewtons, which is 20 to 40 tons. Pretty heavy, so if you take that thing and point it at the ground, it's gonna leave a mark. Okay, so here's some, I love this. This is one of my favorite figures in the whole book. Not that guy, not that guy. This is just showing some initial experiments, and I believe they're burning paraffin here. which,
All like a-
yeah, which is
Isn't that a
a,
wax? Paraffin?
yeah, paraffin is a heavier, heavier
Okay.
hydrocarbon,
That's
but,
what I thought.
again, and I don't see all the instrumentation on here, but you could imagine putting a scale on there to measure how much thrust you're gonna get from this engine before you stick it on a plane.
That could go so bad.
That
could go so bad.
Yeah.
They're really not smart, they're way too close.
Forest
to it.
fire
You see
101.
these sets these days, and everything's all technical.
Yep.
Back then.
Yeah,
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 they're
you
just lighting stuff on fire.
you can put your eye out.
Suits, no
Yep.
I know, yeah, they're all like shielding their faces.
Classic.
That's just like, if you go to, Yellowstone, you have to stand so far back from everything. If
Oh,
when you're in
yeah.
Iceland, you can stand like 2 feet from the hole. You know what I mean? Like, there's no boundaries in Iceland. It's awesome.
So guys, if you take 242, we'll cover the Stirling engine in a little more detail. It's typically all of the working fluid in a Stirling engine stays inside. There's no real exhaust. It's just sort of it's a hot side and a cool side. Kind of wild. I have one in my office. I'll bring it in next time. Here's an example of a Stirling engine just to move air around. Some other more advanced. So here you just have a hot. These are all just mirrors to also just run a Stirling engine. So going straight from sunlight to motion with a working fluid. Again, sunlight to motion with no combustion. Yeah, there it is, Stirling engine. Okay. Oh, and then maybe one last thing. This is kind of a trip. I love looking at these things because they sort of show the peak power density of these different engines. And at some point, you just can't get any more juice out of a steam engine. It reaches a peak. Same thing, internal combustion, and here's jet. Well, what's next? But that's what I like to call mechano-evolution. It's something I used to write about, think about. So.
Yeah, it'll be interesting to see how that, things like that electromagnetic drive that they just came up with, the one that defies the laws there, it's creating thrust through nothing.
Yeah, I'd like to see that too.
Yeah, I watched a video on it and didn't understand it any better at the end of the video.
Okay.
But it's called the EM drive.
Okay. Yeah.
Apparently in space with no resistance, there's no limit to what that can do.
That's what I saw.
Yeah.
I read that, or saw something about that too.
It's a
Okay.
neat thing.
Yeah.
What's that program called that Lori's doing? Because I found her on
FEW.
FEW?
Yeah, food, energy, water, and it's NERT, N-R-T, which is it's another National Science Foundation acronym. I can't remember what NERT stands for, but I'll tell you here in a second. All right, see y'all. Thanks a lot.
Have a good trip.
I will. Thanks. And either Peter or Tim will teach next week.
Cool.
Cover chapter 9.
Oh, well, while you're gone, I'll do some research on